Okay. So, yesterday we started with DFT. So, if the sequence is finite x n 0 1 x 1 dot 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 up to say n minus 1, this is the duration over which the sequence is given. So, it is a finite length sequence, outside it is 0. Sometimes this range is called a support. So, support is finite from 0 to capital N minus 1, over this is defined. So, it is a FIR sequence. Then we have seen that if we take the DTFT and if we plot the DTFT, it is periodic, right. Suppose it is like this from minus pi to pi. You can as well have another period here that goes to 2 pi. So, instead of taking period from minus pi to pi, here we take from 0 to 2 pi. Okay. Any segment of length 2 pi is one period. Okay. Because if you repeat this here again, you get the interwave form. So, either take minus pi to pi and repeat that here, or 0 to 2 pi whatever you have, you go on repeating, you get the same thing. Anyway, so suppose I have got an FIR sequence and this is the DTFT. I made a point yesterday that if the sequence is finite length of capital N number of points, then there is no need to store the entire envelope DTFT, because then we need infinite points on this curve. Okay. Because 0 to 2 pi for omega is a continuous patch. So, there are infinite frequency points and you need infinite values, infinite number of values. So, you cannot store them, but I told you that this is not required. If the length is capital N, you should take n number of samples of this at a sampling period 2 pi by n. So, 0 one sample, then 2 pi by n another sample, then 4 pi by n another sample, dot 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 at 2 pi. So, 0th sample at 0, first sample at 2 pi by n, second sample at 2 into 2 pi by n, that is 4 pi by n, kth sample 2 pi k by n, dot dot dot, it will go up to 2 pi into n minus 1 by n, n minus 1 is sample. So, 0, 2 pi by n into 1, 2 pi by n into 2, 2 pi by n into k, 2 pi by n into n minus 1. Next sample will be 2 pi into n by n, n cancels, which is 2 pi, which is this, because of periodicity is the same as this. So, we will not go up to that. So, we will take here. So, how many samples? 0 to n minus 1. So, total n samples. So, we take n samples, period is 2 pi by n. Okay. This kth sample we denote by k, which is nothing but DTFT at this frequency e to the power j 2 pi this much omega 2 pi k by n. Okay, and that was, if you use the DTFT formula, e to the power minus j omega n, omega is this 2 pi k by n into small n. Okay, and summation over 0 to, not minus infinity to infinity, because sequence is from 0 to n minus 1, outside that is 0. This is called DFT. Then using these samples, that is the samples x k, and k can be 0 1 up to n minus 1. So, these samples, using these samples you can get back your x n. That is, you do not need the entire envelope and then compute inverse DTFT. You can take these samples only, how many, capital N of them, and get back your x n by this formula, that x k, you sum over k, k equal to 0, k equal to 1, like that. So, k also ranges from 0 to n minus 1, and this formula e to the power j 2 pi k small n, here it was minus, it is plus, here it was summed over n, it is summed over k, here small n is your choice fixed from here k was your choice fixed from outside, n also is from 0 1 as given here, n minus 1. This is called inverse DTFT, inverse DFT, IDFT. Okay. So, that means I can get back my original x n from the DFT only. All right. Now, there are several properties which will follow, which we will discuss. Okay. Number 1, if I take this x n, I got the x n. From x n, I can get back the full DTFT by this formula. N equal to 0, of course, 0 to n minus 1. full DTFT. Given any xn, I know full DTFT. But xn I can write in terms of this DTFT samples only, capital Xk. So, if you bring that back here, 1 by n outer summation with respect to small n, inner summation, that is capital the small xn you will replace by this entire summation. Okay. So, n equal to 0 to n minus 1, then xn will be replaced by this entire summation 1 by capital N already taken out. So, we have got xk this much is xn into now okay. This DTFT summation was over n. So, that is remains xn is given xn every time you pick up one small n, that n is fixed. So, x of that n. So, x of that n is this summation 1 by capital N outside this summation where there you put that small n and run the summation over k. So, this will give you xn into this. And now, I told you that in DSP whenever you come across double summation you interchange the two summations. So, it will be 1 by n outside is capital Xk, it depends only on k. So, it comes here n equal to 0 to n minus 1 e to the power this summation minus j omega minus 2 pi k by n into small n. All right, and this is a GP series, because if you consider this to be small a. So, a to the power n, that is a to the power 0, a to the power 1 up to a to the power capital N minus 1. So, this summation will be into 1 minus a to the power capital N, that is a DP series. What is the series? A to the power small n first 0, that is a to the power 0, then a to the power small n equal to 1, that is a to the power 1, a to the power 0 plus a to the power 1 plus a to the power 2 dot 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 up to a to the power capital N minus 1. So, summation will be this elementary GP series formula, and this a value if you substitute, this is x k 1 minus, this is your a. Okay. Okay, a function of this kind. So, that means DTFT can be obtained from its own samples. After all, what is capital X k? K equal to 0, k equal to 1 and k up to k equal to n minus 1 means you are basically taking the whole DTFT itself and sampling it. So, if you know the samples, that is this capital X case, using them you can get back x n, and then therefore, you can get back the DTFT envelope itself. So, DTFT, for DTFT I do not need to store the entire envelope. If I store the capital N number of samples, where n is the length of the original sequence, then using the samples in this formula, by putting those samples in this formula, I can get back my DTFT. So, it is another interpolation formula. Okay. So, this is one property. So, this shows that DTFT itself can be obtained by an interpolation formula of this kind using its own samples. Every sample multiplied by a function like this. Okay. This function, in fact, you can do some manipulation, it is of the form e to the power minus say j theta, you call this angle theta, divided by e to the power minus j say beta, you call this angle beta. So, then you take e to the power j minus j theta by 2. So, it will be e to the power j theta by 2 minus e to the power minus j theta by 2 divided by, again you take e to the power j beta by 2. So, it will be j beta by 2 minus e to the power minus j beta by 2. So, this is twice j sin theta by 2, this is twice j sin beta by 2. So, it basically becomes twice j cancels, okay. E to the power minus j theta plus theta minus beta by 2, okay. So, this much was theta and this much is beta, okay, that by 2. Into sin theta by 2 by sin beta by 2, where theta is this much, this is theta, this much is beta. Okay. Anyway, this shows that DTFT envelope can itself be obtained from its own samples, if the sequence is finite length of n points and I take n number of samples. So, this shows that no need to store the entire DTFT envelope, just most important are the n samples. Using them I can do anything, I can get back original xn, I can get back original DTFT. This is property number 1. Then another question, that suppose some DTFT is given, this DTFT is given, I take this n number of samples, capital X k, that is capital X 0, capital X 1, capital X 2, and then put them in this formula, right hand side, and I get a sequence xn. Now, suppose I allow this small n to go beyond the range, that is, if I think this IDFT inverse DFT formula, so I got these samples from the DTFT, I am putting them here, okay, and I get some sequence. Now, suppose this entire thing is a sequence of duration, originally n from 0, 1, dot n minus 1. Okay, I get some. If you plot this entire thing, it will be a sequence, right, over this duration 0 to n minus 1. But suppose just for fun, just for mathematical fun or game, in this formula I allow small n to go beyond this, okay, to take value capital A, n plus 1, n plus 2 and all that. Then what happens to this formula? Just if we substitute small n equal to something from here, say, for instance, suppose original n was here and you are going to the right to n plus capital N, what will happen? If you bring n plus capital, if you replace n here by n plus capital N, you see what will happen is, this formula will give rise to small n plus capital N, small n plus capital, but capital N and capital will cancel. So, it will be to the power j 2 pi k, okay, n cancels and this is equal to 1. So, what you are left with is this, which is same as this. That means, if this sample is suppose some x n, and now in this formula if I allow small n to go beyond, so jump by capital N, same x n will come here. If I go to n plus 2 n, it will be n plus 2 n means n plus 2 n, 2 n and n will cancel, it will be j e to the power j 4 pi k, again that is 1. So, again you will get back this summation, which is same as this. So, x n will come at n plus 2 n also. So, this way, if the original sequence is here, if your nth point is here, you took the DTFT, then sampled it, you got capital X k and then putting the you are using this capital X k and forming this summation. If small n is from 0 to capital N minus 1, you get back this sequence, right. But if in this summation I allow small n, this right hand side, if I allow small n to go beyond this range, then what will happen? Nth point will come back here at n plus 2n, n plus capital N, same value will come. Okay. Similarly, at capital Nth point, 0, whatever be the value, that will come here, because 0 plus capital N. At 1, whatever is the value, that will come here, okay, and like that. So, this whatever we have, that same thing will repeat, and it will go on repeating. So, it will be a periodic sequence. That means, if you take the inverse DFT, you get the sequence from 0 to capital N minus 1 first. But in the inverse DFT, I now allow small n to take all values from minus infinity to infinity. What you will get is just repetition of this basic period again. Which means, if I give you a periodic sequence, if I give you in the opposite direction, if I give you a periodic sequence, okay, this is one period and same thing is repeating, say, same thing is repeating, this is another period, then again same thing is repeating, like that. So, this is one period, this is another period, and it goes on dot. Then what I do? I take out only this part, okay, one period only, this part, just one period, but from 0 to n minus 1. You call it x n. Then from x n, you find out the DFT capital X k, which is nothing but if you take the DTFT of this, you sample at period of 2 pi n, that is at 0, then 2 pi by n, 4 pi by n, like that, as we have done in the previous case. So, you get capital N number of samples, capital X k, capital X 0, capital X 1 dot, and then you construct, you put them in that inverse formula. If you restrict small n in this formula from 0 to capital N minus 1, you will get this. But if you now allow small n to go from minus infinity to infinity, what we have seen, you will get back periodic repetition of this. That is why this followed by this periodic sequence will come up. That means, giving a periodic sequence, I can represent it by a formula like this. How to get the formula? Take one period from 0 to capital N minus 1, take its DFT, use the DFT in the inverse DFT formula, and then allow small n to take all values. In that case, what we will get is periodic repetition of the basic sequence, basic finite length sequence. Okay. So, this is one way of representing periodic, but infinitely long sequence. You take one period, that is finite length, capital N point, take capital N point DFT, use them in the inverse DFT formula. If you allow small n to be only from 0 to capital N minus 1, you will get back the original finite length sequence. But if you allow now small n to go anywhere, then you get an infinitely long sequence from this formula, but there what we have seen above is that this basic period will keep getting repeated. So, you will get back your original periodic sequence, that will be given by this formula, where small n goes from minus infinity to infinity. There is this periodic sequence, you can take small n anywhere, here, anywhere. Put that small n in this formula, you will get the corresponding sample. Okay, if n is here, and if this much is the sample, take that n here, run the summation, you will get back that. Okay. This is another property. Another very important property is circular shift. We have seen that suppose x n has got a DTFT this. If I shift it by 1 to the right, by k to the right, you will have e to the power minus j omega k times this. Now, I ask a question. Suppose capital X k, which is nothing but sample of this DTFT at 2 pi into k by n at that much omega. 2 pi by n is the basic period, k sample means k times the basic period. So, at that frequency, if you find out the DTFT, that is DFT, discrete Fourier transform DFT, and that we call capital X k. Capital X k is given to you for k equal to 0, 1, 2 up to n minus 1. But suppose I now multiply it by e to the power say minus j 2 pi into k by n and call it x 1 k. If I take the inverse DFT of x 1 k, I will get some sequence x 1 n. I am taking n from 0, 1 to this. That is, I am not making it periodic from minus infinity to infinity, just basic period finite length block is enough. So, I repeat, capital X k came from the original x n, its DTFT was sampled, which gives rise to the endpoint DFT. So, those DFT values capital X k, k could be 0, k could be 1 up to k n minus 1. So, for any k, I multiply it by a complex factor. So, the same k I put here, and this whole thing I call x 1 k. So, x 1 k means I have got x 1 0, x 1 capital X 1 0, capital X 1 1, capital X 1 2 dot dot dot. So, using them I can run the inverse DFT formula and get a new sequence, that will be x 1 n. How is x 1 n related to x n? Okay. Here when I took the DTFT multiplied by e to the power minus j omega k, okay, I got x n minus k, just delayed, shifted. Here if I take x k instead of this DTFT, there is DTFT at omega equal to 2 pi k by n. If I take that and multiply by e to the power minus j 2 pi k by n, okay, that omega. Okay. Then what will be the corresponding sequence x 1 n? That time it was x n minus k, just shifted version by k, but this time x 1 n will be related to x n in which way? Fine. So, x 1 n will be the inverse DFT of this, that is how I got x 1 n, inverse DFT of capital X 1 k. Isn't that the definition I got from here only here. Okay. But x 1 k for any k is this. So, as you run the summation, you bring that factor here, e to the power j 2 pi k by n into small n minus 1. Okay. Now, let us work it out. Suppose we start with n equal to 1. If you put n equal to 1, this is 0. So, it is like the original, what was the original IDFT? What was x n? That was 1 by n summation okay. Now, here I start with n equal to 1 first, n equal to 0 I will do later, n equal to 1. If n equal to 1 is 1 minus 1 0, that is same as this formula with n equal to 0, because x k is present, x k is present, e to the power by j 2 pi k by capital N, e to the power j 2 pi k by capital, all are present. This part is becoming 0, that means here it is n equal to 0, that is this will be x 0. So, x 1 if n is 1, that is same as x 0. Okay. So, x 1 1. So, that means x 0 is getting shifted. Okay. Then take x 1 2, n equal to 2. If n equal to 2, it is 2 minus 1, 1, that is 1 here. So, x 1 dot 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 dot, take n up to Suppose n is capital N, I take n equal to capital N, then what happens? N equal to capital N will be capital N minus 1. Okay. So, x 1 capital N will be okay. But point is capital N x 1 n also is defined from n equal to 0, 1 dot 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 n minus 1. Okay. If I take capital N, the value that we will get, that will be same as the value at n equal to 0, because it is periodic. So, x 1 n is same as, is equivalent to x 1 0, all right. Okay, let me explain. This is the formula, all right. You started with n equal to 1, you got x 0. Okay, that means originally you had x 0, this will go, x 0 will go to point number 1. So, now this much will go here, if it is a will go here. Okay. You just look at it at 0. Now, for the new sequence, this is x n sequence, this is x 1 n sequence. For x 1 n, at point number 1, the value will be same as the original x at point 0. So, this a. Then, if it is b, b will go here, dot 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 at n minus 1 and then n minus 2. Suppose at n minus 2 it is c and then it is d. Okay. See here, if I take n equal to n minus 1, okay, n equal to n minus 1, then that means capital N minus 2. So, the same formula as this, but small n equal to capital N minus 2. So, it will be x capital N minus 2. So, x capital N minus 2, this will go here. So, this is getting shifted here, this is getting shifted here, this is getting shifted here, all right. And last guy, I took this way x 1 n and that was this. You can view it this way also. What is x 1 0? An alternative view, x 1 0. X 1 0 means in this formula 1 by n k equal to 0 to n minus 1 x k e to the power j 2 pi k by n into small n is 0, right. So, 0 minus 1 minus 1. For this, I can add, if I have e to the power j 2 pi here, it will not change anything because e to the power j 2 pi is 1. So, I can bring it here, and e to the power j 2 pi can be written as 2 pi n by n. Okay. In fact, instead of j 2 pi, I can say e to the power j 2 pi into k, because k is an integer. So, e to the power j 2 pi k is 1. E to the power j 2 pi, e to the power j 4 pi, e to the power j 6 pi, they are all 1. E to the power j 2 pi k is 1. Then I can write e to the power j 2 pi k into n by n. So, e to the power j 2 pi k by n I keep outside. So, it becomes e to the power j 2 pi k by n into n minus 1, all right. That is the same formula as this, small n replaced by capital N minus 1. That is x 1 0 is x n minus 1. That means, this guy, there is x 1 0 here, x 1 0 at this point, it will be d x n minus 1. So, this will get, So, it is a circular shift. A goes to right by 1, B goes to right by 1, this goes to right by 1. Last guy does not move further right, it comes back in the original position. So, it is called a circular shift by 1. How it came? If I multiplied the x k dft by e to the power minus j 2 pi into k by n. If now I generalize further, x k is obtained multiplied by e to the power minus j 2 pi by n into k into r, okay, and call it capital X 1 k. Then what will be x 1 n? X 1 n will be by the inverse DFT of this j e to the power j 2 pi k by n into small n, and in this case minus r. So, n minus r outside, right. So, that means you can start this way, x 1, if it is x 1, okay, r is given, r is fixed. So, suppose n is r, so x 1 r, if you put n equal to r, r minus r, that is 0. So, this formula then gives you x 0, x 1 r plus 1, this will give you, if you put n equal to r plus 1, it will give 1. So, this is the formula of x 1 then. If you have this with e to the power j 2 pi k by n into 1, this will give you x 1 dot 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 x 1 say n minus 1. If you have n minus 1, you should have n minus 1 minus r, okay, n minus 1 minus r. So, it is okay. Then x 1 0, x 1 0 means if I put n equal to 0, if I put n equal to 0, then what happens? Okay, I ask you to think about this, and I will join here in the next section. Thank you.